Picture this: you're floating in the pitch-black void of space, tethered to your spacecraft, when suddenly your suit begins to stiffen. The material isn't just cold, it's turning brittle, cracking like glass under the relentless vacuum. Around you, tiny, invisible particles whip past at speeds faster than bullets, piercing through layers of reinforced fabric as if they weren't even there. This isn't science fiction. This is the reality astronauts face every time they step beyond Earth's fragile embrace. Space doesn't just welcome explorers with open arms, it hides dangers so bizarre, so unpredictable, that even the most advanced technology can't always shield us. Most of us grew up dreaming of the stars, imagining space as a silent, majestic frontier waiting to be conquered. But the truth, it's a battlefield. From deadly radiation storms to micrometeoroids moving faster than speeding bullets, the cosmos is packed with hazards that defy our Earth-bound instincts. And here's the unsettling part: many of these threats aren't just rare accidents. They're lurking in every mission, every experiment, every moment humans spend in that infinite darkness. That's exactly why we're diving deep into the 30 hidden dangers of space exploration. Risks so startling, they'll make you rethink everything you thought you knew about venturing beyond our planet. Some of these perils sound like they're ripped straight from a horror movie. Others are so subtle, astronauts don't even realize they're in danger until it's too late. But one thing's certain: by the time we're done, you'll see space in a whole new light, not just as a realm of wonder, but as a place where every triumph comes with unimaginable risks. So buckle up. This journey isn't just about uncovering secrets, it's about surviving them. Cosmic radiation is the invisible killer lurking in the void of space, a danger so pervasive, astronauts can't see it, can't feel it, and yet it's tearing through their bodies every second they spend beyond Earth's protective atmosphere. Unlike the dramatic hazards of Hollywood space disasters, this threat doesn't announce itself with alarms or explosions. It's a silent, insidious bombardment of high-energy particles, remnants of exploded stars, solar flares, and galactic events so powerful they travel across the universe at nearly the speed of light. And when these particles hit human tissue, the damage is catastrophic on a cellular level. Take the Apollo missions, for example. Even on those short trips to the moon, astronauts reported seeing flashes of light behind their closed eyelids, not from sunlight but from cosmic rays slamming into their retinas. Years later, studies revealed those same astronauts faced heart disease rates 5 times higher than Earth-bound counterparts. The reason? Radiation doesn't just pass harmlessly through you. It shreds DNA strands, mutates cells, and dramatically increases cancer risks. Modern astronauts on the International Space Station receive the equivalent of a full-body CT scan every 5 days just from background exposure. But here's what makes cosmic radiation truly terrifying: shielding barely helps. Earth's magnetic field deflects most of these particles, but in deep space there's no such protection. Materials like aluminum, commonly used in spacecraft, actually make things worse. When high-energy particles strike metal, they create a deadly secondary shower of radiation, like shrapnel from a bullet hitting armor. NASA are now experimenting with water-filled walls or even synthetic replicas of Earth's magnetic field, but so far, no solution fully blocks this invisible onslaught. The longer the mission, the deadlier the math becomes. A trip to Mars could expose astronauts to radiation levels surpassing lifetime safety limits in just 18 months. Even inside their spacecraft, they'd face constant bombardment from solar proton events, sudden radiation storms from the sun capable of delivering lethal doses in hours if unprotected. Future colonists might have to live underground, using Martian soil as a radiation shield, turning humanity's greatest exploration into a life spent hiding from the sky. This isn't just a technical hurdle, it rewrites the ethics of space travel. Do we send people to Mars knowing they'll likely develop cataracts, tumors, or cognitive decline years earlier? Cosmic radiation forces us to confront a chilling truth. Space isn't just hostile because it's empty. It's hostile because it's filled with invisible bullets we're only beginning to understand. Solar flares are the universe's version of a tantrum, violent eruptions on the sun's surface that unleash enough energy in minutes to power human civilization for decades. These aren't just spectacular light shows, they're apocalyptic waves of radiation and charged particles, capable of frying electronics, crippling satellites, and delivering lethal doses to anyone caught unprotected in space. And unlike cosmic radiation, which is a constant background threat, solar flares strike without warning, turning a routine mission into a life or death scramble for shelter. Take August 1972, for example. One of the most powerful solar storms ever recorded erupted just months after Apollo 16 returned from the Moon and a mere 9 months before Apollo 17 launched. Had astronauts been in deep space during that event, the radiation levels would have been lethal within hours. Even inside their spacecraft, they'd have faced severe radiation sickness, with symptoms ranging from vomiting and hemorrhaging to long-term organ damage. The timing was so precarious, NASA later admitted it could have ended the Apollo program prematurely with multiple fatalities. Modern spacecraft aren't immune either. The International Space Station has specially designated storm shelters, areas with extra shielding where astronauts hunker down during solar proton events. But these are temporary fixes. A massive flare like the Carrington event of 1859, which set telegraph wires ablaze on Earth, would today devastate satellites, knock out power grids, and leave Mars-bound crews with nowhere to hide. Engineers now design electronics with radiation-hardened chips, but there's no perfect defense when a single flare can unleash 1 billion atomic bombs worth of energy. What makes solar flares especially sinister is their unpredictability. The sun follows an 11-year cycle of activity, but pinpointing exactly when a flare will erupt is nearly impossible. In 2012, a monster flare narrowly missed Earth. A direct hit could have set technology back decades. Future lunar or Martian bases will need underground tunnels or thick regolith walls, turning human habitats into high-tech bunkers just to survive the sun's wrath. This isn't just an engineering problem, it's a logistical nightmare. Mission planners must balance exploration windows against solar maximums when flare risks peak. A Mars colony might thrive for years, only to be wiped out by a single storm. Solar flares force us to confront a humbling reality. Humanity's greatest ventures into space hinge on the mood swings of a star we'll never tame. Floating effortlessly might look like fun, but microgravity is a slow-motion wrecking ball for the human body. Without Earth's constant pull, muscles weaken at an alarming rate. Astronauts can lose up to 20% of their muscle mass in just 11 days, even with rigorous exercise. It's not just about strength fading away. The very structure of bones starts to crumble. Studies show space travelers lose 1 to 2% of their bone density every month, equivalent to decades of aging on Earth. The spine elongates, vertebrae separate, and calcium leaches into the bloodstream, increasing the risk of kidney stones. Imagine returning from a Mars mission only to shatter a hip from something as simple as tripping on a sidewalk. Vision changes are even more unsettling. Over 60% of long-duration astronauts develop spaceflight-associated neuroocular syndrome, where fluid shifts in zero gravity squash the eyeball, flattening its shape and damaging the optic nerve. Some never fully recover their eyesight. Take astronaut Scott Kelly, whose year in space left him with permanently altered vision and genetic changes. 7% of his DNA failed to return to normal. These aren't temporary inconveniences, they're irreversible transformations that rewrite our understanding of human biology. The International Space Station has become a floating lab for these terrifying experiments. Astronauts strap into resistance machines for 2.5 hours daily just to slow the damage, but it's a losing battle. On Earth, even sitting or standing triggers muscle and bone maintenance. In space, the body decides those systems are unnecessary. Future Mars colonists might land too weak to walk, their skeletons brittle as chalk, their eyes struggling to focus on the red soil beneath their boots. Countermeasures are desperate improvisations. Scientists now test artificial gravity through spinning space stations or vibrating plates that trick bones into thinking they're under stress. But these are band-aids on a gushing wound. The brutal truth, microgravity isn't just an obstacle, it's a fundamental redesign of human physiology, proving that space doesn't just change where we live. It changes who we are. Space debris turns Earth's orbit into a cosmic minefield where even a fleck of paint becomes a deadly projectile when it's hurtling at 17,500 miles per hour. That's 10 times faster than a bullet, with enough kinetic energy to punch through solid metal. Think about it. A single screw drifting in low Earth orbit hits with the force of a hand grenade. And right now, there are over 100 million pieces of human-made junk circling our planet, from discarded rocket stages to shattered satellite fragments. It's the ultimate unintended consequence of space exploration. A junkyard we created, now threatening every mission we launch. The 2009 satellite collision was the wake-up call no one wanted. An inactive Russian communications satellite, Cosmos 2251, smashed into an operational American Iridium satellite at a combined speed of 26,000 miles per hour. The impact vaporized both spacecraft, instantly creating over 2,000 new pieces of trackable debris, each one capable of causing another catastrophic collision. This wasn't science fiction. It was the moment orbital debris went from theoretical risk to undeniable crisis. The International Space Station has had to perform emergency maneuvers 32 times since 1999 just to dodge incoming fragments. But here's what makes space debris uniquely terrifying. It's a self-perpetuating nightmare. Every collision creates more debris, increasing the odds of future impacts, a chain reaction known as the Kessler syndrome. If enough junk accumulates, certain orbits could become unusable for decades, trapping humanity on Earth behind a veil of shrapnel. Even tiny objects are lethal. A 1 mm metal shard can disable critical systems, while a 1 cm piece carries the energy of a bowling ball dropped from a skyscraper. The solutions are as complex as the problem. Lasers to vaporize debris, robotic nets to capture it, even magnetic tow trucks to drag wreckage into the atmosphere, all are being tested. But with new mega-constellations launching thousands more satellites annually, the risk grows faster than our ability to clean up. Every mission we send up risks adding to the problem, turning humanity's greatest achievement into its most dangerous legacy. Space debris isn't just a hazard, it's a ticking time bomb we're still learning how to defuse. Isolation in space isn't just physical, it's a slow, grinding erosion of the mind. Imagine being trapped inside a metal can for months, floating farther from Earth than any human in history, watching your home planet shrink to a pale blue dot. The psychological strain of long-duration spaceflight isn't just discomfort, it's a silent crisis, one that could unravel the most disciplined astronaut. Take the infamous Skylab 4 mutiny of 1973. After weeks of relentless work schedules and cramped conditions, the three-man crew snapped. They shut off communications with NASA for a full day, ignoring mission control's calls while they floated in defiance. It wasn't rebellion for the sake of it. It was human nature pushing back against impossible pressure. Later studies revealed the crew had been operating at exhaustion levels comparable to combat soldiers, their stress hormones spiking as the walls closed in around them. The numbers paint an even bleaker picture. Studies of astronauts on the International Space Station show nearly half experience significant mood disturbances, irritability, insomnia, even episodes of depression. On Earth, you can step outside, feel the wind, or call a loved one. In space, you're sealed in a sterile bubble, breathing recycled air with the same faces day after day. The monotony is crushing. Sleep cycles fracture under 16 sunrises a day. Communication delays with Earth stretch to minutes, then hours as you venture farther out. Imagine needing therapy, but your psychologist's replies take 40 minutes to reach you. Mars missions will magnify this tenfold. A round trip could take over 2 years, with crews experiencing what psychologists call Earth out of view phenomenon, a profound existential shift when our planet vanishes from sight. Analog missions on Earth, like Hawaii's HIC's habitat, reveal alarming trends. Crews grow withdrawn, factions form over petty disagreements, and some members stop speaking entirely. The Russian Mars 500 experiment saw one volunteer develop chronic insomnia, rocking back and forth for hours, while another withdrew into near-total silence. Countermeasures exist, but they're banned. Aids on a hemorrhage. Virtual reality headsets simulate Earth environments, but they can't replicate a hug from a child. Crews undergo grueling psychological screening, yet no test predicts how someone cracks after 18 months of canned food and recycled urine. The solution might lie in radical redesigns, rotating crews, shorter missions, even artificial windows projecting real-time Earth views. But one truth remains: space doesn't just attack the body. It rewires the brain, revealing a danger no metal hull can shield against: the fragile human psyche itself. In the brutal environment of space, your life depends on machines working flawlessly, but one tiny glitch can cascade into catastrophe faster than you can scream for help. Equipment malfunctions aren't just inconveniences out there, they're death sentences waiting to happen. Consider Apollo 13, where a simple oxygen tank explosion turned a lunar mission into a desperate fight for survival. 200,000 miles from Earth, with oxygen levels plummeting and carbon dioxide building to lethal levels, astronauts crammed into a freezing lunar module never designed to support 3 people. They jury-rigged air filters using duct tape, plastic bags, and cardboard, improvised fixes that became the difference between life and a silent grave in the void. The Soyuz incidents are even more chilling. In 1971, a faulty valve caused the Soyuz 11 capsule to depressurize during re-entry. The crew, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, died in moments as their air hissed into space, their bodies found perfectly seated at their stations, faces streaked with hemorrhages from the sudden vacuum. Decades later, in 2018, a sensor failure during Soyuz MS-10's launch triggered an emergency abort. The rocket's boosters separated violently, subjecting the crew to 7 Gs of force, like having an elephant suddenly sit on your chest before their capsule plunged back to Earth in a harrowing ballistic descent. Modern spacecraft aren't immune either. In 2020, the International Space Station's Russian segment sprang 3 separate air leaks in less than a year, pinprick holes likely caused by manufacturing defects, each one a reminder that every weld, every seal, every circuit is a potential Achilles heel. Life support systems are so complex that even a single flawed O-ring or cracked coolant pipe can trigger disaster. Every component exists on a knife's edge. Oxygen generators must precisely balance chemical reactions, carbon dioxide scrubbers can't falter, and temperature controls must withstand wild swings between scorching sunlight and utter darkness. Redundancies help, but they're not foolproof. The Space Shuttle had multiple backup systems, yet Challenger still tore apart because of one frozen rubber seal. Engineers now build quadruple redundant systems for critical functions, but weight limits and cosmic radiation make even these prone to freak failures. Future Mars missions face an even grimmer equation: no quick rescues, no emergency resupplies. A broken water recycler or failed airlock seal means watching the clock tick down on your dwindling resources. What makes equipment malfunctions uniquely horrifying isn't just the technology, it's the human factor. Astronauts train endlessly for emergencies, but no simulation captures the soul-crushing moment when your only ticket home starts beeping warnings in a language no one understands. Behind every flashing alarm light is a terrifying truth. In space, there are no hardware stores, no tow trucks, just the cold math of survival against the indifferent machinery keeping you alive. One moment you're baking under unfiltered sunlight hot enough to melt lead, the next you're plunged into shadow so cold your breath would freeze instantly if you could take it. Space isn't just a vacuum, it's the most extreme thermostat imaginable, with temperature swings that can shatter metal and fry circuits within minutes. Imagine stepping from a blazing desert into an Arctic storm, except there's no atmosphere to buffer the transition. Spacecraft don't just need to survive these extremes, they have to maintain a delicate bubble of habitability inside, where a single failed heat vent could mean cooking the crew alive or flash freezing them into human popsicles. Take the moon as a brutal example. In sunlight, lunar temperatures soar to 260 degrees Fahrenheit hotter than boiling water, but step into shadow and they plummet to -280, colder than Antarctica's deepest winter. Apollo astronaut spacesuits had to handle both extremes within minutes as they moved between sunlight and the long shadows of lunar craters. Their visors reflected sunlight like mirrors, while heating coils in their gloves fought against the cold creeping in through their fingertips. Mercury is even more extreme, 800 degrees on the sunlit side, yet -290 in the dark. Spacecraft face a constant tug of war between these extremes. The International Space Station swings from 250 degrees on its sun-facing side to -250 on the shadow side every 90 minutes. Without careful regulation, the station would warp like a soda can left in a campfire, then contract so violently it would crack apart. Engineers use radiators that glow cherry red to dump excess heat, while reflective blankets shield sensitive instruments from solar roasting. But when those systems fail, the results are catastrophic. In 1970, Apollo 13's power down left the command module so cold that condensation shorted out electronics, while the lunar module became stifling as carbon dioxide built up a nightmare of conflicting thermal crises. The real terror comes from how fast these changes happen. On Earth, temperature shifts slowly, oceans and air act like buffers. In space, there's nothing to slow the transition. Materials behave unpredictably. Metals that flex on Earth become brittle as glass, while lubricants evaporate or turn to glue. Solar panels can crack from thermal stress, and fuel lines might freeze solid in shadow, then vaporize when sunlight hits. Future Mars bases will face similar whiplash. Dust storms can plunge temperatures by 60 degrees overnight, while greenhouse habitats risk becoming pressure cookers if cooling fails. Surviving these extremes isn't just about comfort, it's about physics itself betraying you. Every bolt, every wire, every seal is pushed to its breaking point daily. Space doesn't just ignore human technology, it actively tries to dismantle it through the cruelest temperature experiment imaginable. Vacuum exposure is space's most intimate horror. An instant, violent stripping away of everything that keeps you human. Forget Hollywood depictions of exploding bodies or frozen statues. The reality is far more grotesque. In 1965, during a NASA test, a spacesuit leaked in a vacuum chamber, exposing the technician to near-space conditions for 15 seconds. His last conscious memory, feeling saliva boiling off his tongue. That's the first betrayal of vacuum. Your own body turns against you. Without atmospheric pressure, liquids in your tissues vaporize at body temperature. Your skin swells like a balloon but doesn't rupture. Instead, capillaries burst beneath the surface, creating a macabre mapping of internal hemorrhages. Your eyes would feel like they're being sucked outward, tear fluid vaporizing in streaks across your face. Lungs collapse in seconds as air rushes out, not in the opposite of drowning. NASA animal tests in the 1960s showed dogs lost consciousness after 10 seconds, their bowels and bladders evacuating violently as muscles spasmed uncontrollably. But here's what makes vacuum uniquely cruel. You don't die immediately. Soviet experiments with Soyuz spacecraft revealed humans could survive nearly 90 seconds of exposure if repressurized rapidly. In 1971, the Soyuz 11 crew proved this tragically. Their capsule vented during re-entry, killing them silently in their seats as ground control listened helplessly to failing biometrics. Autopsies showed their eardrums ruptured, blood vessels in their brains exploded from pressure differentials, and nitrogen bubbles formed in their bloodstreams like shaken soda. Modern spacesuits are engineered to resist this nightmare, but history shows how easily safeguards fail. In 1982, cosmonaut Valentin Lebedev's suit glove tore during a spacewalk. He felt his hand swelling instantly, the skin stretching against his bones like an overfilled water balloon. Only frantic maneuvering back to the airlock saved him from watching his own body unravel. Future Mars explorers face an even grimmer equation: no quick rescue if a rover suit fails on the surface. You'd have minutes of agonizing awareness as your bodily fluids literally cooked away under the weak Martian pressure, too thin to protect you but just thick enough to prolong the suffering. This isn't just death. It's the complete undoing of human biology, proving space doesn't just kill visitors. It dismantles them molecule by molecule, showing utter indifference to the fragile miracles of blood and breath that sustain us. The greatest threat from alien life might not be towering monsters or invading fleets, but organisms so small they're invisible. Imagine a Mars rover returning to Earth with a stowaway, a microscopic hitchhiker evolved in an entirely different biosphere. Without the checks and balances of Earth's ecosystem, such a pathogen could spread unchecked, exploiting biological vulnerabilities we don't even know we have. This isn't paranoid fiction. NASA's Office of Planetary Protection exists solely to prevent this nightmare scenario. History shows why caution is warranted. When European explorers reached the Americas, they brought smallpox and measles, diseases the native population had zero immunity against. The results were catastrophic: entire civilizations collapsed. Now reverse that scenario. What if astronauts inadvertently bring back a Martian microbe that treats human cells as fertile ground? Unlike earthly diseases, our immune systems would have no evolutionary defense. Even benign extraterrestrial organisms could become deadly if they compete with our gut bacteria or release unfamiliar toxins. The Apollo moon missions took this risk seriously. When Armstrong, Aldrin, and Collins returned, they spent 3 weeks in a sealed quarantine trailer, treated like biological time bombs. Scientists feared lunar dust might harbor dormant pathogens, though we now know the moon is sterile. Mars, however, is a different story. Its ancient riverbeds and subsurface brine pockets could host extremophiles organisms thriving in conditions that would kill earthly life. The Perseverance rover deliberately avoids areas where liquid water might exist to prevent contamination. But contamination works both ways. Human missions could also unleash Earth microbes on Mars, skewing future searches for native life. A single speck of dust from a spacesuit might carry trillions of bacteria, some capable of surviving in Martian soil. This ethical dilemma forces impossible choices. Do we prioritize protecting Earth or preserving Mars' pristine environment? One wrong move in either direction could alter 2 worlds forever. The scariest part: we'd have no warning. An alien microbe might not trigger standard biohazard protocols if it doesn't match known detection parameters. By the time we recognize the threat, it could already be replicating in our crops, our water supply, or our own cells. Space agencies treat planetary samples like level 4 biohazards, the same as Ebola, but absolute containment is never guaranteed. A single crack in a specimen vial, one flawed seal during re-entry, and we're rolling dice with the fate of our biosphere. This isn't just a scientific challenge, it's a philosophical one. How much risk is acceptable in the quest for knowledge? The answer might define not just the future of space exploration, but the survival of life on Earth. Imagine screaming for help and waiting 20 minutes just to hear a response while your oxygen ticks down, your systems fail, and every second stretches into agony. That's the chilling reality of communication delays in deep space. On Earth, radio waves travel at light speed, but across interplanetary distances, even that isn't fast enough. Mars alone can be up to 22 light minutes away, meaning a distress call takes nearly a quarter of an hour just to reach mission control. By the time engineers scramble a solution, another 20 minutes pass before it arrives. 40 minutes total, enough time for a small leak to drain a spacecraft's air supply or a fire to reduce a habitat module to ashes. The Apollo missions flirted with this danger constantly. When an oxygen tank exploded on Apollo 13, Houston's teams worked around the clock to improvise fixes, but every instruction, every piece of guidance, took nearly 3 seconds round trip just because the moon was so close. Multiply that delay for Mars and the math becomes terrifying. A medical emergency, an astronaut suffering a heart attack or a severe injury, would leave crews relying on AI and their own dwindling training. No real-time consultation with Earth's doctors, no live walkthroughs for emergency surgeries. NASA analog missions have proven how dire this gets. During the HIC's Mars simulation, a crew member's simulated ruptured appendix required them to operate using only pre-recorded videos, with latency deliberately added to mimic Martian conditions. The result, a haunting realization: in space, you don't just fight disasters, you fight time itself. Robotic missions face the same peril. The Curiosity rover's 7 minutes of terror landing sequence had to be entirely autonomous. By the time Earth received confirmation the rover had entered Mars' atmosphere, it had already either landed safely or smashed into the surface. Future human missions won't have the luxury of pre-programmed solutions for every scenario. A stuck airlock, a fuel leak, a life support failure. Each becomes exponentially deadlier when every exchange with Earth carries a built-in expiration date. The psychological toll is just as crushing. Isolation studies show humans can endure almost anything with real-time support, but strip that away and stress levels skyrocket. Astronauts reporting a crisis would face an unbearable silence after their transmission, left to wonder if help is coming or if they've already been written off. Soviet cosmonauts in the early days sometimes received updates hours after sending status reports, their missions unfolding in eerie, disjointed time. Solutions are as fraught as the problem itself. Some propose equipping crews with advanced AI capable of diagnosing and solving crises independently, but no algorithm can yet match human ingenuity for novel disasters. Others suggest streaming constant data feeds to Earth, allowing ground teams to monitor situations in near real time. But bandwidth limitations make this impractical for deep space missions. The terrifying truth: communication delays aren't a technical hurdle to overcome. They're a fundamental law of physics, forcing us to accept that in deep space you're truly on your own. Broken bones in space don't just heal wrong, they might not heal at all. On Earth, a fractured leg means a trip to the hospital, pins, plates, and months of careful rehabilitation. But in microgravity, bones don't fuse the same way. Without the constant pressure of weight, the body's repair mechanisms go haywire. Astronauts on the International Space Station have suffered stress fractures from bone loss alone. What happens when someone cracks a rib during a Mars landing, with no surgeon for 34 million miles? Medical emergencies in space aren't just about distance, they're about biology betraying us in ways we're still discovering. Take something as routine as CPR. In zero gravity, the recoil force from chest compressions would send the rescuer floating backward, making it nearly impossible to maintain rhythm or adequate pressure. Even basic procedures turn surreal. An open wound doesn't bleed downward but forms floating spheres of blood that can clog air filters or contaminate equipment. NASA medical kits include staples and superglue for sealing lacerations, but no amount of supplies can compensate for the brutal reality. Space transforms every routine injury into a potential death sentence. Consider the case of astronaut Luca Parmitano, whose helmet began filling with water during a 2013 spacewalk. As liquid crept over his eyes and nose, he fought panic while struggling back to the airlock blind, drowning in his own suit. Had the leak been worse or his reaction slower, ground control could only have listened helplessly as audio cut out. There are no emergency rooms in orbit, no trauma teams standing by. The ISS keeps defibrillators and emergency dental kits, but complex procedures are impossible. An appendicitis attack would require astronauts to administer their own anesthesia and attempt surgery using AI guidance, a nightmare scenario tested only in simulations. Pharmaceuticals behave unpredictably too. Medications degrade faster in radiation-rich environments, and microgravity alters how drugs distribute in the body. Painkillers might become less effective, while antibiotics could fail entirely if bacteria evolve resistance in the closed habitat. Even diagnostic tools are compromised. Ultrasounds float away before capturing clear images, and standard blood tests assume Earth's gravity for accurate readings. Future Mars missions plan for telemedicine, but the 20-minute communication delay makes real-time guidance impossible. Crews will rely on AI like the European Space Agency's Simon, a floating robot assistant loaded with medical protocols. But when seconds count, a severe allergic reaction, a sudden cardiac event, no algorithm can replace human expertise. The cruelest twist, the very stress of isolation and danger increases the likelihood of medical crises, creating a vicious cycle where the need for care rises as access vanishes. This isn't just about stocking better first aid kits. It's about rewriting the rules of medicine for an environment where the human body becomes its own worst enemy, and help is always too far away. Hunger in space isn't just about an empty stomach. It's a slow unraveling of the body and mind when every calorie counts double. On Earth, running low on food means a quick trip to the grocery store. In space, it's a countdown to disaster with no resupply for millions of miles. Astronauts aboard the International Space Station consume around 3,000 calories daily, but even that carefully calculated number hides a grim reality. Much of their food loses nutritional value over time. Vitamins degrade in radiation, proteins break down, and after 6 months, some meals become little more than flavored paste. The Russian Mir space station gave us a terrifying preview of what happens when supplies run thin. In 1997, a Progress resupply ship missed its docking, leaving the crew with rationed portions for weeks. They stretched every meal rehydrating freeze-dried soups with meticulous care, crushing crumbs to avoid wasting a single gram. But the real danger wasn't just hunger pangs, it was the cognitive decline. Studies show malnutrition in microgravity accelerates muscle and bone loss while impairing decision-making, a lethal combo when one wrong move could rupture a spacesuit. Water scarcity is even more dire. The ISS recycles about 90% of its water through urine and sweat purification, but the system is fragile. A single malfunction in 2013 left astronauts relying on emergency reserves for days, rationing showers to 30 seconds of mist. On Mars, where resupply is impossible, colonists might mine ice deposits, but if those sources contain toxic perchlorates, dehydration could become a slower, more agonizing threat. Menus designed for efficiency often backfire psychologically. NASA early missions featured bite-sized cubes coated in gelatin to prevent crumbs, a texture so revolting, astronauts barely ate. Modern improvements include tortilla, as instead of bread, no crumbs, and occasional fresh fruit deliveries via cargo ships. But during the 2011 Soyuz launch delay, crews faced months of repetitive meals, triggering appetite loss that bordered on starvation. The math for a Mars mission is chilling. A 3-year round trip would require over 12,000 pounds of food per person, impossible with current launch capacities. Solutions like hydroponic gardens sound promising until you realize one power failure could wipe out an entire crop. Every lettuce leaf grown on the ISS represents hours of labor cleaning roots, adjusting lights, all for a salad that provides mere fractions of daily nutrients. This isn't just about packing more granola bars, it's about confronting a brutal equation. In space, every bite you take is a brick removed from your spacecraft's hull, every sip of water a trade-off against fuel weight. Survival means walking a knife's edge between enough and never enough, where the line between sustenance and starvation is as thin as the aluminum shielding keeping the void at bay. Fire in space doesn't spread, it blooms. On Earth, flames rise predictably as hot air lifts them upward. But in microgravity, fire becomes an alien phenomenon, spreading in all directions like a slow-motion explosion of glowing tendrils. The 1997 Mir space station fire revealed just how quickly this beautiful, deadly phenomenon can spiral out of control. A malfunctioning oxygen generator ignited, filling the module with choking smoke and eerie, spherical flames that clung to surfaces instead of dissipating. Astronauts fought the blaze with wet towels, their emergency masks barely filtering the toxic fumes, fully aware that in a sealed metal can 250 miles above Earth, there's no escape route marked exit. The physics behind space fires are counterintuitive. Without gravity pulling cooler, denser air downward, oxygen doesn't replenish at a flame's base. Instead, combustion creates a bubble of exhausted gases that smothers the fire from within unless fresh oxygen drifts into contact, creating unpredictable flare-ups. NASA experiments aboard the International Space Station show candle flames burning at temperatures hundreds of degrees lower than on Earth, yet forming strange blue orbs that linger for minutes. A single spark could float unseen until hitting an oxygen-rich pocket, then erupt without warning. What makes fire especially treacherous aboard spacecraft is the abundance of accelerants. Modern stations use oxygen concentrations around 30% higher than Earth's 21 to compensate for lower cabin pressure. Combine that with Velcro, fabric, and plastic insulation, and you've built a perfect storm. The Mir crew reported flames spreading along cables like a fuse, while molten metal droplets floated through the air, each one capable of starting secondary fires. Their extinguishers could only spray limited amounts of liquid. Too much would create floating fuel globules, making the inferno worse. Safety protocols now include flame-resistant materials and compartmentalized modules, but astronauts train for worst-case scenarios that would chill any Earth-bound firefighter. Picture trying to smother a fire when your extinguisher's recoil sends you drifting backward, or watching embers float into air vents that distribute them throughout the station. Future Mars habitats face an even grimmer calculus: no emergency evacuation possible, no fire department en route. A single electrical short could doom an entire colony, their only choice to watch as their oxygen literally burns away. The ultimate horror isn't just the flames, it's the aftermath. Smoke doesn't rise in space, it forms a lingering fog of carcinogenic particles. After the Mir incident, the crew spent days scrubbing soot from every surface with makeshift filters, knowing each inhaled particle was trapped in their lungs forever. Fire in space leaves no safe haven, not even the air you breathe. The air inside a spacecraft should keep you alive, but sometimes it turns traitor. Confined in a sealed metal bubble, every exhale, every chemical reaction, every machine hum adds invisible toxins that can creep up like a silent assassin. Carbon dioxide is the most insidious offender. On Earth, trees and ocean currents scrub it away effortlessly. In space, it pools around astronauts like an invisible fog, waiting to scramble their brains. During the Apollo 13 crisis, crew members watching CO2 levels climb toward lethal limits had to jury-rig air filters using plastic bags and tape, because in space, even the act of breathing becomes a countdown against chemistry. But CO2 is just the beginning. Ammonia leaks from cooling systems can burn lungs and corrode equipment before anyone smells the danger. In 2013, astronauts aboard the International Space Station woke to emergency alarms, a toxic ammonia spill from external cooling loops. While the leak was outside the habitable modules, it underscored how one ruptured pipe could force crews into gas masks and emergency protocols with nowhere to evacuate. Even mundane activities generate lethal byproducts. Soldering electronics releases formaldehyde, while off-gassing from plastics builds up in recycled air like a slow poison. Histories near misses read like horror stories. The Soviet Soyuz 21 mission in 1976 ended abruptly when cosmonauts reported a noxious odor later, suspected to be nitric acid fumes from faulty thrusters. They abandoned Salyut 5 station just in time, their headaches and nausea worsening by the hour. Decades later, space shuttle missions carried canaries in coal mine-style detectors, color-changing patches that would darken if toxic gases like hydrazine rocket fuel leaked into the cabin. The real nightmare lies in detection lag. Many dangerous gases are odorless below lethal concentrations. Mercury vapors from broken instruments, ozone from electrical arcs, even excess oxygen, which turns metals flammable all, can hit deadly levels before sensors trigger alarms. Modern spacecraft use complex scrubbers and redundancies, but Mars-bound crews face an added terror of planetary dust. Lunar regolith nearly poisoned Apollo astronauts when they tracked it inside, a fine powder that sticks to lungs like asbestos and reacts with moisture to form corrosive compounds. Martian soil, rich in perchlorates, could do far worse if inhaled during habitat breaches. Survival hinges on constant vigilance. Astronauts train to recognize the first symptoms: tingling lips from CO2, metallic taste from ammonia, knowing their lives depend on catching threats before the air itself becomes their executioner. 1 degree off course might not seem like much on Earth. A wrong turn means backtracking a few blocks. But in the endless black of space, that same tiny miscalculation can mean sailing past your target planet entirely, with no roadside to pull over and recalculate. Navigation errors don't just delay space missions, they erase them. Consider the haunting case of NASA Mars Climate Orbiter in 1999, a $327 million spacecraft that disintegrated because one engineering team used metric units while another used imperial. A single software glitch converted thrust calculations incorrectly, sending the probe 60 kilometers closer to Mars than planned, where atmospheric friction ripped it apart. All because of numbers on a screen. The Apollo missions teetered on this knife's edge constantly. During Apollo 11's descent to the Moon, Armstrong and Aldrin suddenly spotted boulders strewn across their landing zone, their trajectory slightly off from simulations. With fuel for just 40 seconds of hover time, Armstrong manually piloted the lunar module to safety, his pulse spiking to 150 beats per minute. Had he overcorrected, underadjusted, even their save was a gamble. Decades later, analysis revealed they'd overshot by 4 miles. A trivial error on Earth, but on the Moon, it nearly stranded them in impassable terrain with no hope of rescue. Deep space magnifies these risks exponentially. Unlike Earth navigation, where landmarks and GPS provide constant course checks, interstellar travel relies on inertial guidance systems, delicate assemblies of gyroscopes and accelerometers that track movement relative to a starting point. One flawed calibration, one corrupted star tracker reading, and the error compounds over millions of miles. Voyager 2's 1989 Neptune flyby was accurate to within 24 miles, but only because engineers spent weeks tweaking its trajectory using barely detectable Doppler shifts in its radio signal. Without those corrections, it would have missed the planet entirely, its discoveries lost to the void. The cruelest twist: there's no reverse in space. Misjudge a course correction and the fuel spent can't be reclaimed. In 2003, Japan's Hayabusa probe nearly ran out of propellant after a trajectory error forced it to chase its asteroid target like a drunk stumbling after a moving train. Modern missions use gravity-assist slingshotting around planets to save fuel, but these demand millimeter precision. One mistimed approach at Jupiter could fling a probe into the Sun instead of toward Saturn, as happened to Pioneer 6 in the 1960s. Future Mars colonists face an even darker scenario, navigating without real-time Earth support. A dust storm obscuring the Sun or a failed gyro could leave crews blindly adrift in the descent phase, their landing ellipse stretching from safe plains to sheer cliffs. Soviet Mars probes in the 1970s often vanished during this blackout period. One veered so far off course it likely skipped off the Martian atmosphere and into solar orbit, a ghost ship still wandering the cosmos. This isn't about flawed technology, it's about the universe's indifference to human error. Space doesn't forgive, it doesn't offer second chances. One overlooked decimal, one misaligned antenna, and the equations of motion conspire to carry you forever beyond the reach of home. A speck of dust shouldn't be terrifying until it's moving 10 times faster than a rifle bullet. That's the chilling reality of meteoroid strikes in space, where objects smaller than a grain of sand pack enough kinetic energy to punch through steel. While massive asteroids dominate disaster movies, the true menace lies in these invisible fragments, remnants of comet tails or shattered asteroids, drifting unseen until they collide with a spacecraft at orbital velocities. The 2013 Chelyabinsk meteor was a wake-up call. A house-sized rock, undetected until it exploded over Russia with 30 times the energy of Hiroshima, its shockwave shattering windows 600 miles away. Now imagine that impact concentrated into a marble-sized projectile moving twice as fast. The International Space Station bears the scars of these cosmic bullets. Its solar panels are peppered with microscopic holes, while reinforced modules like Zvezda have replaced windows after strikes left spiderweb cracks. In 2016, a 7mm fleck punched a chip into the station's cupola window. Had it been slightly larger, the pressurized compartment could have decompressed in seconds. NASA tracks over 23,000 orbital debris objects, but meteoroids are far harder to predict, some streaking through at 50,000 miles per hour. Unlike deliberate space junk, these natural projectiles follow no set path, turning every mission into a game of Russian roulette with the cosmos. Historical near misses read like thriller plots. In 1969, Apollo 12's command module endured a meteoroid storm so intense, astronauts reported sparkles flashing outside like fireworks. Later analysis showed hundreds of impacts on their hull. Gemini 4's crew returned with a cratered heat shield from a strike that, had it penetrated, would have turned re-entry into a fireball. Even unmanned craft aren't safe. Europe's Copernicus Sentinel-1, a satellite, was nearly crippled in 2016 when a millimeter-sized particle disabled part of its power system. Modern spacecraft use Whipple shields, layers of aluminum and Kevlar spaced apart to fragment incoming particles, dissipating their energy like a bulletproof vest. But these defenses have limits. A pea-sized meteoroid striking at orbital speeds hits with the force of a hand grenade, enough to breach multiple shield layers. The real nightmare scenario: a pinhole leak too small for alarms to detect immediately, but steadily venting air until the crew notices their oxygen gauge dropping. Future deep space missions face even greater peril beyond Earth's protective magnetosphere, where meteoroid flux is 3 times higher. Lunar or Martian colonists won't just worry about habitat breaches, they'll fear secondary impacts, where meteoroids striking the surface launch volcanic sprays of debris at hypersonic speeds. NASA lunar modules were designed to withstand sand grain impacts, but Mars' thinner atmosphere offers less burning protection than Earth's. This isn't just about dodging rocks, it's about confronting an unsettling truth. Space doesn't care about human ingenuity. A random speck of ancient stardust, invisible until the moment of impact, could undo billions in technology and years of preparation. Every spacecraft launched is essentially hurling itself into a cosmic shooting gallery, hoping statistics stay on its side. But in the infinite expanse of space, luck has a way of running out. Artificial gravity sounds like the perfect fix for all those muscle-wasting, bone-crumbling effects of weightlessness until you realize we're trying to cheat physics itself. Picture the classic sci-fi solution: a spinning space station creating centrifugal force to pin astronauts to the walls like clothes in a dryer. But engineering this isn't just about building a rotating tin can, it's about tricking human biology into accepting a lie. Too slow, and the Coriolis effect turns every head movement into a nausea-inducing roller coaster. Too fast, and the force differential between your head and feet could literally rupture blood vessels. NASA early experiments with short-radius centrifuges left test subjects vomiting after minutes, their inner ears rebelling against the unnatural spin. The health trade-offs are brutal. While artificial gravity might save bones and muscles, it introduces new nightmares. Prolonged exposure to even 2 times Earth's gravity could strain hearts into hypertrophy, while lunar or Martian gravity, 1/6 and 1/3 of Earth respectively, might offer no meaningful protection against deterioration. The Soviet Bian satellites revealed that rats exposed to partial gravity still suffered muscle atrophy, their cells seemingly programmed to expect Earth's unrelenting pull. Future Mars colonists could find themselves stuck in a no-win scenario, stay too long in reduced gravity, and their bodies weaken irrevocably, return to Earth, and their hearts might fail under the sudden load. Even the mechanics of spinning habitats hide devious traps. A Stanford torus design proposes a mile-wide rotating wheel, but construction at that scale in microgravity defies current technology. Smaller designs risk gravity gradients where your feet feel heavier than your head, potentially causing blood to pool uncomfortably in the legs. Astronauts testing NASA Armstrong spinner reported disorientation so severe they couldn't walk straight for hours after stopping. And what happens when the rotation must halt for docking or repairs? Crews would endure alternating bouts of weightlessness and artificial gravity, their bodies caught in a vicious cycle of adaptation and whiplash. Then there's the psychological toll. Humans evolved with a constant downward pull. Our balance, our intuition, even our plumbing assumes gravity's presence. A rotating environment messes with fundamental perceptions. Toss an object sideways and it appears to curve unnaturally. Water poured from a floor-level faucet would seem to defy physics as the station spins beneath it. Early experiments with rotating rooms on Earth showed subjects struggling with basic tasks, their brains refusing to reconcile the conflicting cues. Now imagine living like that for years, where every dropped item becomes a trigonometry problem. Current solutions are stopgaps at best. The International Space Station's tiny centrifuge module was scrapped due to vibration issues, leaving astronauts to rely on resistance exercises that barely slow the damage. Private ventures like Orbital Assembly propose rotating space hotels, but their designs gloss over the brutal reality. We don't know what long-term partial gravity does to human reproduction, child development, or aging. Lunar colonists might watch their children grow with brittle skeletons, never strong enough to visit their parents' home planet. This isn't just an engineering puzzle, it's a fundamental redesign of human existence. Artificial gravity offers salvation from space's ravages, but at a cost that could reshape our species in ways we're only beginning to fear. Stepping outside a spacecraft isn't just a walk in the park. It's a high-stakes dance with death where every second counts. Spacewalks or extravehicular activities are arguably the most dangerous routine tasks astronauts perform, a fact hammered home by the near disaster of Luca Parmitano in 2013. Floating 250 miles above Earth, his helmet began filling with water from a clogged cooling system, the liquid creeping over his nose and eyes until he was effectively drowning in the void. Blind and disoriented, he had to rely on memorized handholds to drag himself back to the airlock, his muffled breaths the only sound in his water-filled helmet. This wasn't an isolated incident, it was a stark reminder that in the vacuum of space, even the most routine tasks can turn lethal in an instant. Suit malfunctions are just the beginning. The very design of a spacesuit is a precarious compromise between mobility and survival. Pressurized to mimic Earth's atmosphere, these bulky garments stiffen like inflated balloons, turning simple movements into exhausting struggles. Apollo-era astronauts found their gloves so rigid they returned with fingernails torn off from constant pressure against the hard interiors. Modern suits aren't much better. NASA's EMU design, first introduced in the 1980s, still requires astronauts to pre-breathe pure oxygen for hours to avoid decompression sickness, a painful condition where nitrogen bubbles form in the bloodstream. But the real terror lies in what happens when these technological marvels fail. In 1965, during the first American spacewalk, Ed White's suit overheated so severely his visor fogged completely, leaving him stranded outside Gemini 4 until his oxygen ran dangerously low. Tethers, those lifelines keeping astronauts connected to their spacecraft, have their own horrifying failure modes. During a 1991 Soviet spacewalk, cosmonaut Alexander Volkov's tether snagged on an antenna, leaving him dangling helplessly until his partner maneuvered close enough to free him. Had it snapped, he would have drifted into orbit, a ghost forever circling Earth. Even today, NASA plans for such nightmares. Astronauts train to enter a stable Y position, using small jets to stop uncontrolled spins if their tether breaks. But these emergency maneuvers require split-second reactions most humans can't muster under panic. The environment itself is a minefield of unseen threats. Sunlight in orbit is unfiltered, heating one side of a suit to 250 degrees while the other side plunges to -250. Materials behave unpredictably in these extremes. Lubricants evaporate, metals fuse, and plastics crack. In 2007, astronaut Rick Mastracchio's glove tore during a spacewalk, exposing his hand to vacuum for terrifying seconds before he could retreat to the airlock. Had the tear been larger, his blood would have boiled at body temperature, his tissues swelling like overfilled balloons. Perhaps most chilling are the what-ifs we've barely confronted. A micrometeoroid could puncture a suit silently, the astronaut unaware until their oxygen gauge starts dropping. A faulty thruster pack might send someone careening away from their ship with no hope of return, as dramatized in the film Gravity, a scenario NASA classifies as a contingency EVA with no guaranteed recovery. Future missions to Mars or asteroids will amplify these risks exponentially. Where rescue is impossible and even communication delays mean ground control can't offer real-time guidance. Spacewalks represent the ultimate paradox of exploration. To unlock the universe's secrets, we must repeatedly risk everything in a realm that shows no mercy. Every zipped suit, every clipped tether, every cautious handhold is a gamble against physics itself, one where the house always wins eventually. Running out of fuel in space isn't like stopping at the side of an empty highway, it's a one-way ticket to drifting forever. Propellant isn't just how spacecraft move, it's the difference between coming home and becoming a tomb orbiting the sun. The Apollo 13 crew understood this better than anyone. After their oxygen tank exploded, they had to use the lunar module's engines designed for a gentle moon landing to slingshot around the moon and back to Earth. A single overburn or misfire would have sent them hurtling past Earth into the void, their oxygen running out long before rescue could reach them. modern missions face even tighter margins. The Dawn spacecraft, which explored asteroids Vesta and Ceres, had to meticulously ration its ion thrusters. One wrong calculation and it could have missed orbit entirely, becoming just another speck lost in the asteroid belt. Even the Mars rovers risk running dry not on gas but on power. Opportunity's final message in 2018 wasn't dramatic. It was a fading whisper as dust-covered solar panels failed to recharge its batteries. That's the silent horror of fuel limitations, death by degrees, systems shutting down one by one until silence takes over. The terror lies in the physics. Unlike cars, spacecraft can't coast to a stop. They follow orbital mechanics with brutal precision. In 2010, Japan's Akatsuki probe missed Venus orbit by a heartbeat when its main engine choked during a critical burn. It spent 5 years adrift before engineers could improvise a second chance using tiny attitude thrusters. Had that failed, Akatsuki would have circled the sun endlessly, a $700 million monument to one misfire. Even successful missions flirt with disaster. Cassini's 20-year Saturn Odyssey required 92 precisely timed engine burns, each consuming precious hydrazine. Mission planners juggled trajectories like a chef balancing ingredients, knowing one extra correction might leave the probe unable to defend itself against Saturn's gravity. The final plunge into Saturn's atmosphere wasn't just poetic. It was the only way to ensure Cassini wouldn't crash into and contaminate moons like Enceladus, where it might have destroyed potential alien ecosystems. Future deep space explorers won't have the luxury of rescue plans. A Mars mission carrying humans will need enough fuel for course corrections, emergencies, and the return trip, but every extra pound of propellant means less room for food, water, or shielding. One engine failure, one unexpected detour around a solar storm, and colonists might gaze at Earth through their windows, close enough to see continents but destined to starve before they could ever walk on them again. This isn't just about running out of gas. It's about the unforgiving arithmetic of space travel, where every drop of fuel is measured against the weight of a human life, and the only thing harder than reaching the stars is making sure you can still come back. Solar wind doesn't howl like a storm. It creeps, an invisible tide of charged particles gnawing at everything in its path. Day after day, year after year, these atomic bullets, mostly protons and electrons streaming from the sun at 1,000,000 miles per hour, chip away at spacecraft surfaces like cosmic sandpaper. The damage isn't dramatic like a meteoroid strike, but that's what makes it so insidious. Unlike the instant violence of an impact, solar wind erosion works in slow motion, degrading materials until one day, critical systems simply fail without warning. Take the Hubble Space Telescope's original solar arrays. After just 4 years in orbit, engineers noticed a startling drop in power output. Inspection revealed the array's delicate metal coatings had been thinned by relentless solar wind bombardment, their atoms literally knocked loose particle by particle. This wasn't a design flaw. It was space itself acting as a universal solvent, dissolving human technology at the atomic level. Modern satellites now use protective coatings like indium tin oxide or multilayer insulation, but even these merely slow the inevitable. The process behind this erosion is deceptively simple. Solar wind particles carry enough energy to knock atoms out of solid materials through a phenomenon called sputtering. Imagine a cue ball striking a racked set of billiard balls. Each collision sends atoms flying. On spacecraft, this means critical components like wiring, optics, and thermal coatings gradually lose mass. The Voyager probes, now in interstellar space, have had their camera lenses eroded to near opacity after decades of exposure. They're iconic golden records designed to last 1 billion years. The engraved grooves holding humanity's message could be smoothed away long before any alien civilization finds them. Even more alarming is how solar wind interacts with spacecraft materials in unexpected ways. The International Space Station's massive solar panels were designed to withstand this barrage, but engineers discovered the constant particle flow creates electrostatic discharges, tiny lightning bolts arcing across panel surfaces. Left unchecked, these discharges can fry sensitive electronics or trigger false alarms in navigation systems. Modern panels now include microscopic grooves to disrupt charge buildup, a stopgap solution that adds weight and complexity. Mars missions face a double threat. Unlike Earth, the red planet lacks a global magnetic field to deflect solar wind, leaving spacecraft exposed to the full fury of the sun's output. Worse, Martian dust storms loft fine particles high into the atmosphere, where solar wind charges them electrostatically. NASA InSight lander found its solar panels covered in this charged dust, which clung tenaciously, reducing power output far faster than predicted. Future colonists might watch their habitat's outer layers flake away like sunburnt skin, with no way to stop the decay. The cruelest irony: the very regions richest in solar energy, close to the sun where solar panels work best, are where erosion hits hardest. NASA Parker Solar Probe, flying through the sun's corona, endures temperatures hot enough to melt steel while its carbon composite shield slowly vaporizes. Each orbit leaves it lighter than before, a grim reminder that in space, even the energy that powers us is also what destroys us. This isn't just a material science problem, it's a countdown against physics itself. Every spacecraft ever launched is engaged in a silent, unwinnable war of attrition against a star that will outlast all our creations. The solar wind doesn't rage or roar. It whispers atoms away one by one, patient as eternity, until nothing remains but skeletal frames orbiting long-dead instruments. The mind wasn't built for the endless black. Isolated in the void, deprived of Earth's rhythms, even the most disciplined astronauts report eerie distortions, voices whispering in empty modules, phantom shadows flickering at the edge of vision, the unsettling sense of being watched by something just out of sight. These aren't just fatigue-induced mirages, they're the brain's desperate rebellion against sensory deprivation on a cosmic scale. Soviet cosmonauts on early Salyut missions dubbed it the phantom presence effect, with multiple crews reporting vivid hallucinations of deceased loved ones or surreal landscapes superimposed over the stars. One described smelling freshly cut grass inside the sterile metal cabin, a sensory ghost of Earth so intense it brought him to tears. The Apollo program had its own brushes with this phenomenon. On Apollo 11, Buzz Aldrin reported fleeting moments of disorientation where the moon's horizon seemed to warp, as if the lunar surface itself was breathing. Later missions documented astronauts experiencing time dilation seconds stretching into subjective minutes during high-stress maneuvers, a side effect of the brain's struggle to process inputs in an environment devoid of familiar cues. Scientists now attribute these episodes to the break-off phenomenon, where the brain, starved of Earth's sensory anchors, starts fabricating its own reality. But the most profound psychological shift is the overview effect, a term coined after astronauts described sudden, overwhelming epiphanies when viewing Earth from orbit. Unlike hallucinations, this is a radical shift in perception. Astronaut Edgar Mitchell of Apollo 14 spoke of an explosion of awareness where national borders vanished, and he felt an intense connection to all life. Others report uncontrollable sobbing or existential awe so visceral it rewires their worldview permanently. The effect isn't just emotional, it's physiological. Brain scans of astronauts post-mission show altered activity in the parietal lobe, the region that processes spatial orientation and self-perception. The terrifying flip side: not all cosmic revelations are blissful. Some experience the reverse overview effect, a crushing sense of Earth's fragility amplifying their isolation. Canadian astronaut Chris Hadfield described staring into the infinite void and feeling like a speck on a speck, a perspective so destabilizing he had to consciously refocus on instrument panels to avoid spiraling. Mere crews reported space stupor, staring vacantly at viewports for hours, their minds trapped between wonder and existential dread. Future Mars colonists will face these trials without the comforting blue marble in their window. Studies in Antarctic isolation, where winters plunge stations into months of darkness, show alarming rates of depressive episodes and dissociative states. Add the knowledge that home is now an unreachable dot in the sky, and the psychological toll could fracture even the most resilient minds. NASA now trains astronauts to recognize these symptoms, but no protocol can fully armor the human psyche against the universe's indifference. This isn't just about seeing things that aren't there, it's about the slow unraveling of reality's seams when stripped of Earth's sensory touchstones. Space doesn't just distort metal and bone, it warps perception itself, revealing a chilling truth. The final frontier isn't just outside the spacecraft. It's inside the astronaut's skull. Lunar dust isn't just dirt, it's razor-sharp glass on a microscopic scale, forged by billions of years of meteoroid impacts fracturing the moon's surface into jagged particles. When Apollo astronauts first tracked this abrasive powder into their landers, it clung to everything like electrostatic sandpaper, grinding at seals, jamming zippers, and even wearing through the layers of their spacesuits. Buzz Aldrin described it as having a charcoal-like smell when disturbed, an unsettling reminder that this wasn't Earth's benign soil. It was a hostile substance actively working against human technology. The dust structure, untouched by wind or water erosion, retains knife-edged fractures that make it exponentially more destructive than terrestrial sand. In a sealed environment, it becomes airborne for hours, infiltrating electronics and lung tissue alike. The health effects revealed themselves swiftly. Apollo crews reported lunar hay fever, burning eyes, congested sinuses, and throat irritation after inhaling trace amounts. Later analysis showed the particles were small enough to embed deep in alveolar tissue, where their glass-like edges could cause long-term damage similar to silicosis, an industrial lung disease. And without Earth's moisture or atmospheric processes to blunt their edges, these particles never soften. Lunar dust retrieved from Apollo missions remains as sharp today as the moment it was collected, a silent testament to its enduring menace. Mars presents an even darker twist. Martian regolith isn't just jagged, it's laced with perchlorates, toxic salts that can trigger thyroid dysfunction and wreak havoc on human physiology if ingested. NASA Phoenix lander confirmed their presence in 2008, detecting concentrations high enough to poison unprotected colonists, but the real horror lies in the dust's mobility. Mars' thin atmosphere and frequent storms allow particles to stay suspended for months, coating solar panels and infiltrating habitats. Unlike lunar dust, which sticks via static, Martian dust is fine enough to slip past conventional air filters, creating a slow-motion toxic exposure. Equipment suffers equally. During Apollo 12, fine dust coated camera lenses and thermal control surfaces, forcing astronauts to wipe them constantly. The abrasive grit infiltrated the lunar module's mechanism so thoroughly that some switches nearly failed. Future missions won't just battle mechanical wear, they'll face electrostatic discharges caused by dust clinging to sensitive electronics, potentially short-circuiting life support systems. NASA Perseverance rover already contends with this, its instruments requiring regular cleaning modes to shake off accumulated particles. Solutions remain painfully inadequate. Magnetic filtration could trap some iron-rich lunar dust, but Mars perchlorates demand chemical scrubbing. Spacesuit designs now include dust mitigation systems, like vibrating flaps to shake off particles, but none address inhalation risks during seal breaches. The cruel paradox, the very act of exploration kicks up more dust, ensuring that every footstep, every rover wheel, every mining operation exacerbates the problem. This isn't just a cleaning challenge, it's a slow, creeping threat that could sabotage long-term colonization. Lunar and Martian dust doesn't just dirty boots. It reshapes the lungs of those who breathe it, grinds away the machinery keeping them alive, and turns humanity's greatest outposts into death traps disguised in ruddy, innocuous powder. Time dilation sounds like science fiction until you realize it's the universe's cruel joke on deep space travelers. Thanks to Einstein's theory of relativity, time doesn't tick at the same rate everywhere. The faster you move or the stronger the gravity you're near, the slower your clock runs compared to someone else's. For astronauts on a long mission to Mars or beyond, this isn't just physics trivia. It could mean returning to an Earth that's aged years more than they have. Imagine bidding farewell to loved ones only to land back home and find their children older than you are. The Apollo astronauts experienced this on a minuscule scale. Their high orbital speeds meant they technically returned to Earth a few microseconds younger than if they'd stayed behind. But on interstellar voyages, the effect becomes staggering. A hypothetical mission to Proxima Centauri at 90% light speed would subject the crew to severe time dilation. While they might experience just 4 years of ship time, over 8.5 years would pass on Earth. Miss a birthday call, and you could return to find your family has moved on, assuming you were lost forever. Even within our solar system, the discrepancies add up. A Mars-bound astronaut traveling at higher speeds might find their watch drifting out of sync with mission controls by milliseconds each day. Over a multi-year mission that could compound into seconds, enough to throw off precision maneuvers if not accounted for. GPS satellites already correct for relativistic effects, adjusting their clocks to stay in sync with Earth, but human missions introduce biological complications. The body's internal rhythms, from circadian cycles to cellular aging, wouldn't match the outside world's timeline. The psychological toll could be devastating. Isolation studies show humans cling to shared timekeeping as a lifeline, celebrating holidays, counting mission days, watching Earth seasons change in real-time transmissions. But relativity mocks that stability. A message sent from Earth might take minutes to reach Mars, but the sender's perception of time is also subtly different. Over decades, colonists might feel unmoored from humanity's collective rhythm, their lived experience diverging from everyone they left behind, the worst part. There's no fix. This isn't a technical hurdle, it's woven into the fabric of spacetime itself. Future explorers won't just brave distance and danger, they'll surrender the very idea of synchronized time, becoming temporal exiles in a universe indifferent to human clocks. Jupiter doesn't just loom large in the night sky. It's a radioactive nightmare wrapped in lethal magnetic fields powerful enough to fry electronics and cook human tissue in minutes. Unlike Earth's gentle magnetosphere, which deflects most cosmic radiation, Jupiter's magnetic field is a monster 18,000 times stronger than our planet's, trapping charged particles in belts so intense they'd deliver a fatal dose to an unshielded astronaut in under an hour. These aren't just theoretical hazards. When NASA Galileo probe dove into Jupiter's orbit in 1995, its hardened electronics still took a beating, with radiation levels so extreme they altered the spacecraft's memory systems mid-mission. The math behind Jupiter's radiation is chilling. The planet's inner radiation belts pack electrons and protons accelerated to nearly light speed, creating an environment where radiation doses hit 3,500 rems per hour, enough to kill a human 10,000 times over. To put that in perspective, a single hour near Jupiter's core belts would absorb more radiation than an entire career spent on the International Space Station. Even Europa, Jupiter's icy moon and a prime target for life-seeking missions, orbits deep within this kill zone. Its surface receives 500 rems per day, a yearly dose that would guarantee cancer for anyone standing on its frozen plains unprotected. Historical missions reveal just how ruthless Jupiter's radiation can be. Pioneer 10, the first spacecraft to brave the planet's magnetic fury in 1973, suffered multiple system failures as high-energy particles bombarded its circuits. Juno NAS, a recent orbiter, barely survived its polar orbits thanks to a titanium vault shielding its electronics, a design that still couldn't prevent sporadic data corruption. Future probes aiming for Europa or Ganymede will need similar armor, turning spacecraft into high-tech fortresses just to endure a few months of operation. But here's the cruel twist: Jupiter's radiation isn't static. Solar storms and volcanic activity from Io, Jupiter's hyperactive moon, inject fresh plasma into the belts, creating unpredictable spikes in intensity. The Ulysses spacecraft in 1992 detected one such surge, a particle storm so violent it would have obliterated unshielded instruments. Human missions venturing here wouldn't just face a constant haze of radiation. They'd gamble with sudden, invisible flares capable of piercing even robust shielding. Solutions are as daunting as the problem itself. Some propose using Jupiter's own moons as radiation shelters, parking spacecraft in the shadows of Ganymede or Callisto during high-intensity periods. Others envision ships with liquid hydrogen, barriers, a material that blocks radiation effectively but requires impractical volumes for crewed missions. The bitter reality: Jupiter's radiation belts aren't just obstacles, they're a permanent barricade, reminding us that some corners of the solar system might remain off-limits to flesh and blood explorers. Cryogenic fuels don't just power rockets, they demand a Faustian bargain with temperature extremes so severe they bend the laws of material science. Picture liquid hydrogen, the same propellant that thrusts spacecraft beyond Earth's grasp, chilling to -423 degrees Fahrenheit, colder than the void of space itself. At these temperatures, ordinary metals turn brittle as glass, seals shrink and leak, and even the air we breathe condenses into frosty slush. But the real horror lies in what happens when these supercold fluids warm up even slightly. A single degree of heat gain transforms dormant liquids into expanding gases with terrifying force. In 1965, a Saturn rocket test turned catastrophic when a hydrogen leak met an ignition source, detonating with enough power to hurl a 40-ton launch umbilical tower 300 feet. The explosion wasn't just fire, it was a shockwave of vaporized metal and concrete, proving that cryogenics don't just fail, they retaliate. The physics behind these disasters is deceptively simple. Cryogenic fuels like liquid hydrogen and oxygen must stay at unearthly lows to remain liquid, requiring tanks wrapped in layers of vacuum-sealed insulation. But any breach, a hairline crack from thermal stress, a faulty valve seal allows ambient heat to rush in. As the liquid warms, it expands 700 times its original volume, building pressure until containment fails explosively. NASA X-33 program learned this brutally in 2000 when a composite hydrogen tank ruptured during testing, shredding the prototype with a boom heard miles away. Unlike conventional fuels that burn, cryogenic explosions are more like detonations, pressure bombs with no warning flare. Handling these fuels is a high-stakes ballet of precision. During space shuttle launches, ground crews wearing specialized freezer suits capable of withstanding temperatures that would flash freeze flesh in seconds monitored every connection for frost buildup, a telltale sign of leaks. Even then, tragedy struck. In 2007, an explosion at a SpaceX test site injured several technicians when a nitrogen purge system failed, allowing oxygen to mix with helium in a piping network. The resulting blast wasn't from the propellants themselves, but from the systems designed to control them, a vicious reminder that in cryogenics, even the safety measures can turn deadly. Spacecraft face even greater risks. The Centaur upper stage, a workhorse of orbital delivery, uses pressurized helium to push cryogenic fuels into engines. But if helium bubbles form in the fuel lines, they can trigger violent water hammer effects, rupturing pipes mid-flight. In 1966, an Atlas Centaur rocket disintegrated seconds after launch when a helium bubble collapsed, creating a pressure spike that tore the vehicle apart. Modern designs include elaborate baffles and anti-vortex systems, but as SpaceX's 2016 Falcon 9 pad explosion proved, a single faulty strut in a helium tank can still cascade into a fireball worth $300 million. The cruelest twist, these fuels remain indispensable. Liquid hydrogen packs more energy per pound than any other propellant, making it the only option for deep space missions. NASA Artemis moon rockets guzzle it, as will future Mars ships. Every launch is a gamble with thermodynamics itself, balancing unthinkable cold against the vacuum's unforgiving heat. Engineers layer tanks like Russian nesting dolls, insulation within insulation, but the margin for error is razor thin. A solar flare warming a tank by 10 degrees, a micrometeoroid piercing a vacuum layer, even an electrical spark from static buildup. Any could ignite an inferno where flames burn invisible in pure oxygen, leaving no warning until metal melts. This isn't just about handling dangerous chemicals. It's about wrestling with substances that defy human intuition, where a splash on unprotected skin causes frostbite faster than liquid nitrogen, and a whiff of leaking hydrogen disperses odorless until it's concentrated enough to detonate. Cryogenics don't just power our way to the stars, they're a reminder that some technologies demand tribute in risk for every ounce of thrust they give. Human error doesn't announce itself with warning lights or alarm bells. It slips in silently, riding on fatigue, stress, or the tiniest lapse in judgment. In space, where every action is magnified by the unforgiving environment, a single mistake can rewrite mission objectives from triumph to tragedy in seconds. Consider the chilling case of Soyuz 23 in 1976. While attempting to dock with the Salyut 5 space station, cosmonauts Vyacheslav Zudov and Valery Rozhdestvensky missed a critical detail in their approach calculations. Fatigued after days of cramped conditions and mounting pressure, they inadvertently activated their descent sequence mid-dock, plunging their capsule into a brutal emergency re-entry that ended with them crashing through the ice of a frozen lake in -22-degree weather. The error lasted seconds. The consequences nearly cost them everything. The psychology behind these moments reveals an uncomfortable truth. Human brains aren't wired for space's relentless precision. NASA studies of astronauts' cognitive performance show reaction times slow by up to 20% during prolonged missions, while memory recall falters under stress. The infamous Mars Climate Orbiter disaster in 1999 wasn't caused by some exotic space phenomenon. It was a mundane unit conversion error between imperial and metric measurements that slipped through multiple layers of review. Teams on the ground, overwhelmed by deadlines, failed to catch the discrepancy until the probe had already disintegrated in Mars' atmosphere. The price tag: $327 million vaporized by a mistake anyone could make during a late-night spreadsheet session. Fatigue amplifies these risks exponentially. During the harrowing Apollo 13 crisis, astronaut Jack Swigert's exhausted oversight nearly became catastrophic. Asked by Mission Control to stir the oxygen tanks, a routine procedure, he flipped the wrong switch sequence momentarily, causing a voltage spike that ignited wiring insulation. While the tank's existing damage was the root cause, this momentary lapse could have accelerated disaster. Modern space stations implement human factors engineering, color-coded controls, tactile feedback buttons, even scent markers, but no design can fully eliminate the specter of exhaustion. The International Space Station's just-in-time checklist system forces astronauts to pause and verify each step, yet near misses still occur. In 2015, a crew member accidentally activated a fire suppression test sequence instead of a communication routine, triggering alarms station-wide. Perhaps most unsettling are the errors we'll never know about, the near catastrophes caught purely by chance. Soviet archives reveal that during the 1985 Salyut 7 crisis, when the station went completely dead, ground controllers initially misdiagnosed the problem as a simple power glitch. Only a last-minute recheck by a sleep-deprived engineer caught the true issue. a cascading electrical failure that would have made the station unrecoverable. Had he nodded off that night, 2 cosmonauts would have arrived at a frozen tomb instead of performing their legendary repairs. The solutions are as complex as human nature itself. NASA now employs exhaustion shadow crews, ground teams who mirror astronauts' sleep schedules to catch fatigue-induced mistakes before they're transmitted to orbit. AI Overwatch systems cross-reference every command against thousands of failure scenarios in real time. But for missions beyond Earth's orbit, where communication delays rule out instant ground support, crews will face an unrelenting truth. In space, perfection isn't just expected, it's the fragile barrier between survival and oblivion. Atomic oxygen in space doesn't rust metals like Earth's humid air. It devours them molecule by molecule, a silent feast playing out in the vacuum. Up where the atmosphere thins to almost nothing, individual oxygen atoms, split apart by solar radiation, become hyper-aggressive scavengers. Unlike the oxygen we breathe, these lone atoms are missing electrons, making them desperate to bond with anything they touch. When they collide with spacecraft surfaces at orbital speeds 17,500 miles per hour, they don't just settle on the metal. They slice straight into it, breaking molecular bonds and transforming sturdy materials into flaking, weakened shadows of themselves. The effect is like sandblasting, except instead of sand, it's a relentless rain of invisible, hungry particles carving away at your hull. The first signs of this insidious damage appeared on early space missions. When NASA retrieved the Long-Duration Exposure Facility satellite after 6 years in orbit, engineers were stunned. Multi-layered insulation blankets designed to reflect heat looked like they'd been through a shredder. Their shiny aluminum coatings oxidized into powdery white dust. Solar panels lost up to 10% of their efficiency as their protective glass layers etched away under the atomic onslaught. Even materials considered space-proof, like Captain, a gold-colored plastic used in insulation, developed a sandpaper texture as oxygen atoms gnawed through its polymer chains. The damage wasn't cosmetic, it was a structural time bomb. What makes atomic oxygen so devastating is its selectivity. It ignores some materials while voraciously attacking others, like a termite with a taste for specific woods. Silver, prized for its conductivity in electronics, erodes 20 times faster than aluminum. Molybdenum disulfide, a common lubricant, turns into brittle molybdenum oxide, leaving moving parts to grind themselves into failure. The International Space Station's older modules show this wear clearly. Their once smooth surfaces now pitted and dull, like an old car left out in a hailstorm. Engineers initially underestimated the threat, assuming the thin atomic oxygen concentration couldn't possibly matter. They were wrong. Countermeasures exist, but they're imperfect. Satellite manufacturers now coat vulnerable components with silicon dioxide or other barrier layers, but these shields themselves degrade over time. The Hubble Space Telescope's original solar arrays, replaced in 1993 after just 3 years, were retrofitted with sapphire-reinforced panels to resist erosion, an expensive but necessary fix. Private companies are experimenting with self-healing materials infused with compounds that react with atomic oxygen to form protective crusts. But these solutions add weight and complexity to already fragile systems. The cruel irony, this corrosion accelerates during solar maximums periods when the sun's increased activity should theoretically help spacecraft by thickening the upper atmosphere and slowing orbital decay. Instead, the extra solar energy splits more oxygen molecules into ravenous single atoms, doubling or tripling the erosion rate. NASA Materials International Space Station experiment has spent decades testing samples outside the ISS, revealing another nightmare. Atomic oxygen doesn't just attack in straight lines. It creeps into microscopic cracks and under edges, exploiting weaknesses humans can't even see until it's too late. Future missions face a grim calculus. Lunar and Martian dust may prove abrasive, but at least they're visible threats. Atomic oxygen works invisibly, relentlessly, like a carpenter ant colony hollowing out a house's wooden beams while the owners sleep. Station crews can replace degraded parts, but deep space probes bound for Jupiter or beyond, they'll carry this slow-motion death sentence with them, every exposed wire, every thermal blanket, every critical surface gradually turning to dust in the cosmic wind. The lesson is humbling. Space doesn't just attack with dramatic meteoroid strikes or explosive decompression. Sometimes destruction comes one nearly invisible atom at a time. Solar panels are the lifelines of space exploration until they fracture, degrade, or simply stop converting sunlight into power. Unlike Earth, where power grids offer backup upon backup, spacecraft and stations rely entirely on these fragile arrays to keep oxygen flowing, systems running, and heat shielding operational. When they fail, darkness doesn't just mean inconvenience, it triggers a countdown to catastrophe. In 2010, the International Space Station narrowly avoided a power crisis when one of its 8 solar array wings suffered a partial short circuit, reducing output by nearly 25%. Engineers scrambled to reroute systems, delaying experiments and forcing astronauts to ration power. Had another panel failed simultaneously, the station could have faced rolling blackouts in critical modules, life support systems flickering off one by one like candles in a draft. The threats to solar panels in space are as varied as they are brutal. Micrometeoroids punch microscopic holes in photovoltaic cells, creating dead zones where electricity should flow. Atomic oxygen erodes protective coatings, leaving the delicate silicon beneath exposed to further damage. Even sunlight itself becomes an enemy over time. The same photons that generate power also degrade the panel's efficiency, with performance dropping roughly 1% per year from ultraviolet bombardment. The Mars Opportunity rover's slow demise in 2018 wasn't just due to dust storms blocking the sun. Years of UV exposure had already weakened its panels, making them unable to recover once the skies cleared. Worse still, solar panel failures often cascade. When one cell in an array cracks or delaminates, the lost current forces adjacent cells to work harder, overheating them and accelerating their decline. During the Skylab mission in the 1970s, a micrometeoroid shield tore loose during launch, taking one of the station's solar arrays with it. The remaining panels were stretched beyond capacity, their output dwindling as temperatures inside the station soared to a sweltering 130 degrees Fahrenheit. Astronauts had to jury-rig a makeshift sunshade and operate in dim, oven-like conditions for weeks, a preview of how quickly power loss snowballs into life-threatening crises. Repairs are no simple feat. Spacewalking to replace damaged arrays is among the most hazardous tasks astronauts undertake. In 2007, during a daring ISS panel repair, a solar array suddenly flexed, tearing along its length like a zipper and nearly striking spacewalker Scott Parazynski with a whip crack of metal and wiring. Even routine maintenance risks electric shock. Solar panels can't be fully de-energized while exposed to sunlight, leaving technicians to work on live circuits hundreds of volts strong. Future deep space missions won't have the luxury of Earth-orbiting resupplies. A cracked panel on a Mars-bound vessel might mean watching your power margins shrink day by day, darkness creeping closer as your life support reserves dwindle to nothing. The cruelest irony: the farther a mission travels from the Sun, the less effective solar panels become. Jupiter receives just 4% of the sunlight Earth does, forcing probes like Juno to rely on enormous, ultra-efficient arrays that still generate barely enough power to run a handful of household appliances. Europa Clipper, NASA's upcoming mission to Jupiter's icy moon, will carry solar panels spanning over 100 feet, each one a potential single point of failure in an environment where replacement is impossible. This isn't just an engineering challenge, it's a silent war against entropy itself. Every photon captured, every watt generated, comes at the cost of the panel's own slow destruction. Space doesn't offer second chances when the lights go out. There are no emergency generators, no extension cords stretching back to Earth, just the cold equations of energy in versus energy out, and the terrifying knowledge that survival depends on glass and silicon thinner than a playing card. Radiation doesn't just burn skin or scramble DNA, it silently hollows out your bones, attacking the very factory that produces your lifeblood. Deep inside marrow, where stem cells tirelessly churn out red and white blood cells, cosmic rays and solar particles unleash chaos at a microscopic level. Unlike the dramatic radiation sickness seen in nuclear accidents, marrow damage creeps in unnoticed until suddenly, your body can't fight infections, carry oxygen, or even clot blood from a simple cut. NASA studies of astronauts returning from long missions reveal a chilling trend. Their blood samples show significantly reduced hematopoietic activity, as if someone turned down the dial on their body's ability to replenish itself. The science behind this breakdown is as brutal as it is precise. High-energy particles from galactic cosmic rays don't just pass through tissue, they leave trails of ionization, shredding the delicate architecture of bone marrow like shrapnel through a nursery. Stem cells, which lack the protective mechanisms of mature cells, are especially vulnerable. Research from particle accelerators simulating space radiation shows that a single heavy ion strike can obliterate entire clusters of these progenitor cells, creating dead zones in marrow where blood production simply stops. Over time, the cumulative effect mimics accelerated aging, leaving astronauts with immune systems decades older than their chronological age. History offers grim previews of what happens when marrow fails. Victims of the 1999 Tokemura nuclear accident in Japan, exposed to similar high-LET radiation found in space, developed pancytopenia, a catastrophic drop in all blood cell types. Without transplants, they succumbed to infections their bodies could no longer recognize, let alone fight. While astronauts face lower doses, the protracted nature of space exposure poses a unique threat. Marrow doesn't get a chance to recover between radiation hits, leading to progressive exhaustion. Mice exposed to simulated space radiation at Brookhaven National Lab developed chronic anemia, their marrow visibly scarred and shrunken under microscopes. The human body's response makes the situation worse. Damaged stem cells often enter a state called senescence alive but non-functional, clogging up marrow space like broken machinery in a factory. Worse, they emit inflammatory signals that further disrupt healthy neighboring cells. It's a double betrayal. Not only does radiation destroy blood producers, it turns some into saboteurs. Astronauts on the International Space Station already show elevated inflammatory markers, suggesting this insidious process may already be underway during standard missions. Shielding offers little comfort. While Earth's magnetic field deflects most charged particles, materials like aluminum on spacecraft actually worsen the problem for heavy ions. When these high-energy particles strike metal shielding, they generate dangerous secondary radiation, a spray of fragmented nuclei that amplifies the damage. NASA research into polyethylene and water-based shielding shows promise, but no current technology can fully block galactic cosmic rays without adding impractical mass. Even the best-protected Mars-bound crews would absorb enough radiation to risk permanent marrow suppression over a 2-year mission, the terrifying implication. Space anemia might be just the beginning. Marrow doesn't just make blood, it's also home to mesenchymal stem cells that maintain bones, cartilage, and even fat stores. Radiation-induced damage could explain why astronauts suffer such severe bone loss, their skeletons crumbling from lack of maintenance as much as disuse. Future colonists might face a horrific trifecta: weakened bones that fracture easily, insufficient blood cells to heal the breaks, and an immune system too compromised to prevent infections in the wounds. Countermeasures remain agonizingly theoretical. Drugs like Plerixafor, used to mobilize stem cells in cancer patients, could potentially help replenish damaged marrow, but they've never been tested against space radiation's unique effects. Experimental therapies involving stem cell infusions or even pre-mission marrow extraction and storage face enormous ethical and logistical hurdles. The bitter reality is that bone marrow, that unassuming tissue hidden in our skeletons, may prove to be the Achilles heel of deep space exploration, a silent casualty in the body's invisible war against the cosmos. The greatest terror of space isn't the dangers we've catalogued, it's the ones we can't even imagine. For all our planning, our equations, our simulations, the cosmos remains a vast repository of mysteries that could shatter our understanding of physics, biology, and survival in an instant. Take the eerie phenomenon of dark comets, hypothetical objects theorized to emit no visible light, drifting unseen until they're upon us. Unlike traditional comets with their glowing tails, these stealthy projectiles could strike without warning, their trajectories impossible to track until gravitational perturbations betray their presence. Imagine a spacecraft torn apart by an object astronomers never saw coming, its wreckage spinning into the void before mission control even registers the impact. Then there's the enigma of fast radio bursts, cosmic signals so powerful they release more energy in milliseconds than the sun does in days. Their origins remain hotly debated, colliding neutron stars. Alien propulsion, whatever the cause, a burst pointed at Earth could fry satellites and electronics like an EMP from the depths of the galaxy. In 2020, astronomers detected one such burst from our own Milky Way, raising unsettling questions. What if a closer burst hit a Mars-bound crew, scrambling their navigation or life support systems beyond repair? Deep space may also harbor biochemical nightmares. On Earth, toxic substances follow predictable rules: arsenic poisons, mercury accumulates. But what if an alien microbe thrives on elements we consider inert, or excretes compounds that corrode our habitats like acid? The Viking landers' controversial 1970s experiments hinted at possible Martian metabolism unlike anything in our textbooks. Future colonists might face pathogens that don't trigger immune responses because they're so alien. Our bodies wouldn't recognize the invasion until it's too late. The cruelest unknown, physics itself might behave differently out there. Quantum anomalies, pockets of altered spacetime, even theoretical void creatures from cosmology's wildest hypotheses, none can be ruled out. Soviet cosmonauts in the 1960s reported unexplained visual phenomena now studied as light flashes in space, some theorizing cosmic rays interacting with the visual cortex. But what if they glimpsed something beyond our models? This is the chilling frontier of space exploration. No matter how many dangers we anticipate, the universe always keeps a few cards hidden. Every mission is a roll of the dice against forces we don't yet have names for, where the next lethal surprise might rewrite the rules of survival itself. We've journeyed through 30 hidden terrors lurking in the void, from cosmic rays shredding DNA to solar flares frying electronics, from bone-melting microgravity to psychological fractures in isolation. Each threat reveals the same hard truth: space isn't just empty, it's actively hostile, armed with traps both obvious and unimaginable. Yet here's the paradox that defines our species: knowing all this, we still reach for the stars. Apollo astronauts stared down radiation storms on their way to the moon. ISS crews repair air leaks while orbiting at 17,000 miles per hour. Mars rovers persevere through dust storms that would suffocate a human in minutes. These aren't just engineering challenges, they're invitations to evolve. Every danger forces innovation. Water-walled shields against radiation, artificial gravity experiments, even bioengineered crops that could survive toxic Martian soil. The solutions often ripple back to Earth. Scrubbers developed for spacecraft now purify air in hospitals, while crash-resistant materials inspired by lunar landers protect cars. Space's cruelty becomes humanity's curriculum, teaching us to build tougher, think smarter, and adapt faster. But survival demands more than technology. It requires a shift in how we explore. Future missions must balance ambition with humility, recognizing that space won't bend to human will. We must bend to its rules. That might mean accepting slower travel to shield crews, or designing habitats that mimic Earth's rhythms to preserve mental health. Perhaps the greatest danger isn't any single threat, but the arrogance of underestimating them all. Now we turn to you, the pioneers watching from Earth. Which of these 30 dangers keeps you awake at night? The silent creep of radiation, or the sudden violence of a hull breach? The loneliness of interstellar isolation, or the nightmare of a medical crisis with no hospital within 60 million miles? Share your thoughts below, because the next era of space exploration won't be shaped by astronauts and engineers alone, but by everyone bold enough to stare into the void and ask, how do we conquer this? The cosmos has shown its teeth, now let's show our ingenuity.